you work then, for instance, you can work with the Dirac equation. This is spin-orbit coupling. You can exactly take it into account in DFT because it's a one-particle coupling. So then instead of starting with the Schrödinger equation, you just take the Dirac equation. And this is in fact how we do that. You can take the Dirac equation, or then you can use, depending on what kind of basis you use here, you can use this, the second variational principle and introduce the spin-orbit coupling perturbatively, depending on which problem you are dealing with, okay? But spin-orbit coupling is not a problem.
It has to include spin directly.
Yes, so the issue is that, of course, you have to pay, as soon as you put spin-orbit coupling, you lose spin as a good quantum number. So therefore, you have to work with the basis where you have now L coupled to S. But this is not where DFT is not working. DFT is not working in this, only in this term here. Any interaction that is on-site, no problem. Okay? So I can tell you more if you want later on about that. So, okay, let me see what do we do with this exchange correlation functional. And the simplest approximation, which was also proposed by Kohn and Sham, is the so-called local density approximation. What does the local density approximation do? Okay, so the idea is basically to write your exchange correlation functional in terms of basically an integral of local exchange correlation functionals, where this local exchange correlation functional is taken from an exact solution of the basically the homogeneous electron gas. So let me tell it maybe in another words. There is one system that we know we can solve exactly. We can solve the Schrödinger equations exactly, and this is the homogeneous electron gas. And this is what Serperly and Adler did a long way back. You can, by quantum Monte Carlo, you can solve this problem exactly. So the idea is, okay, let me take from this problem, let me subtract all these terms that I was showing to you here. I'm subtracting these terms, and I'm getting at the end an exchange correlation functional for this problem. And what I'm going to do is I'm going to use this information here. For every density in my problem, I'm going to put this exchange correlation functional and integrate it over all n of r, and then this is the exchange correlation functional for my problem. This works extremely well for metals. And it makes sense because in metals we have a strong screening of Coulomb repulsion, and therefore to make this approximation is a good approximation. It doesn't work well for Mott insulators, it doesn't work well for systems where correlations are very strong. Okay? But this is the simplest approximation, and as I say, it has had a lot of, and it still has a lot of success in applying it. So, okay, so now we have the ingredients, and now we have to solve these equations. And what is important here is my pointer. The point is that in density functional theory, this is a theory that has been developed for many, many years, and there are codes around that people can use, codes that you press the button. So basically you put the crystal structure that you want to deal with, press the button, get the results, and you use that. And I really very strongly would like to give an advice. This is not the way of doing density functional theories. You have to know what you are doing, otherwise you can do really a lot of wrong things. So when one says do a density functional, you have to know what you are doing, so you have to really go into these codes and understand what the code is doing. Otherwise, you may do a lot of wrong things, because it's not that easy as just pressing a button. There are many parameters that you have to take. So do a density function instead of running one. So that was basically the advice. So now, how do we do this? How do we do now these calculations? So we have to solve these equations, okay? And you see that this is a kinetic term. This is the basically the external potential, so the interaction with the ions. This is my Hartree term that depends on the density, and this is my exchange correlation functional. I will choose an exchange correlation functional, and then I basically have to do these derivatives. So now what I have to do is, let me start by, I have to choose a basis. So to solve this equation, I have to choose in which form these wave functions should have. This would be my starting point, and therefore I have many choices. And here I'm just mentioning some choices. The simplest one, the most unbiased one. So if you are given a problem that here is your equation for a system of your electrons in your lattice, the most unbiased basis would be plane waves. So you just choose a basis of plane waves and work with plane waves in order to solve these equations. So this, in fact, indeed is the most unbiased basis, but is extremely, extremely expensive to work with plane waves. So it's not really the best way to solve these equations. You can go to the completely opposite limit and say, okay, I am describing basically crystals, so the electronic structure of a crystal, where I have my atoms are ordered in a certain symmetry, and I know very well how to deal, for instance, with a hydrogen atom. I know how the electrons in a hydrogen atom, so the electron, or hydrogen or helium, I know how to describe the wave function of this electron in hydrogen. Why don't I use this information for describing the electrons in my system? So this is the other extreme, which is the so-called localized atomic orbitals, where you put the information here of your atoms, of your electrons that are basically belonging to a certain atom in the crystal. And there is a third option, which is what is called the atomic sphere methods. Here, basically, it uses the concept of scattering theory, so that if you think about electrons that are moving into a crystal, they are scattering through the potential of your ions, and you use these concepts of scattering theory to build up your basis. So let me show you two examples. One is which are a compromise between these different cases that I was showing to you. So this is my crystal. This is my crystal, and what I did now here is where are my atoms sitting, and what we do is we partition basically the space where, so think about, that we are describing either in real space, or we will go, because we have periodic systems, we will go to the K-space, but let me start with the real space. So basically here's where my atoms are sitting, and I want to describe, of course, the wave functions of my electrons in all the space. So I divide the space into the spheres around my atoms, and interstitial is the space which is between the spheres. And what I'm going to do is, if I am away from the atoms, I expect in the interstitial, basically the electron, I can describe it as a plane wave. And this is what we are doing here. So the electron in the interstitial is being described as basically plane waves. And when I am here, my wave function is here near the atom, I'm going to use the information that I know from the hydrogen atom. So I'm going to use it in terms of basically these radial functions and spherical harmonics, which is what you know from hydrogen. And the only thing you have to pay attention to when you make these composite wave functions is that you have to apply continuity when your wave function basically goes from the sphere to the interstitial. So continuity conditions. So this is the way you now start by using your basis. A different basis here is these Muffington orbitals, which is what I was mentioning to you. You use the concept of scattering theory. So basically you work with Bessel functions inside the sphere and inside the sphere and outside the sphere. And again, you have to impose the conditions of continuity. So this basis, for instance, is the basis that it's being used in codes like Vin2K, ELK, these codes that you can get and perform calculations with them. So basically, it's with this basis. Okay, so we chose a basis. What do we do with it? So let me go now and see the flow of equations that we have. You have to tell me how much time? So 10 minutes, no? 10 minutes. So, what do we do? Okay, I chose my basis. For instance, let's say that I take this augmented plane wave. So I write, and now here is where comes the information of my crystal. So what do I want to describe? For instance, I want to describe lanthanum 2 copper 04, okay, the parent compound of the high-density superconductor. So I take the structure, this is a perovskite, I give this information, so I have the units, I give the information of the unit cell, basically. So my unit cell has this copper, this oxygen, this lanthanum, and they are positioned in this place in the unit cell, and then I build the corresponding wave functions with this information of which atoms, which electrons, and where they position. And I start by first just building the density, the electron density with this information of my initial crystal. So this will be my initial guess. I go there into my set of equations, and now the first thing I have to do with this initial guess, of course I have to calculate. Remember that my equation had all these potentials that were depending on the density, so therefore I calculate first the potentials that come into my equation, and once I have the potentials with this initial guess, I solve the Kohn-Sham equations that I was showing to you. And here I will get, in fact, the eigenvalues is what we call the Kohn-Sham energies, and since we are having, these are all block-life wave functions, I'm going to have, of course, the K dependence in the Brillouin zone. So we solve these equations, and now we again calculate the density with, you know, when you are going to solve this equation, you are going to obtain a new set of wave functions. So now you take your wave functions, you sum them up, and you obtain a new density for describing your system. Now what you do is you compare the new obtained density with the old one that you started, and you have to now to choose some criteria to decide whether this is good enough. So usually what you want in self-consistency is you are going to compare always the new obtained density with the previous one, and you arrive to consistency when they basically are not changing anymore. So you go, and if they are too different from each other, again, you put again the new density into your process, you calculate potentials, you solve the equations, until, and you make this process, it can be 20 iterations, it can be 10 iterations, until you reach self-consistency. And once you reach self-consistency, here it is, you have now the information of the density of your system. And you know from the Hohenberg-Kohn theorem, as soon as we have that, we can start calculating all the properties that we want for my system. And we not only have the density, because of construction, we also have the wave functions, so we can now use this information to describe the electronic properties of my system. Let's take here, for instance, one of these iron-based superconductors, the one that I was showing to you, this 1111, and now what I'm plotting here is basically these Kohn-Sham energies, which I'm going to make this jump to say these are the Kohn-Sham energies for my electron system, and I'm plotting them as a function of basically in the Brillouin zone by choosing a path. And what we see here is the Fermi level. So what do these band structure tell me? So basically what I'm plotting, let me go back, I'm plotting these solutions. This is all what I'm doing. I'm plotting these solutions in K-space. And here is the Fermi level. So here is basically the energy up to the field where I have field electrons. So what we see now is, okay, let me look. Here's Z to gamma. So Z to gamma, it means I would be going in this direction. And you see that basically near the Fermi level, which is what I am interested in because I want transport properties, it's basically there is no dispersion. It's a flat band. So in the flat band, it means basically there is the electron, there is no dispersion, and this is what I would expect, because along this direction there is no much movement of the electrons. The electrons are mostly in these two-dimensional planes here, okay? Because these are so basically these are mostly D bands, D and arsenic. The bands of lanthanum and oxygen are all filled or empty. They don't play a role except for charge transfer. Okay, so now let me go, here I'm showing the Fermi surface, so I just did this cut and look what is empty, and so these would be empty pockets, which are these ones here, so we call it Hall pockets, and now I just go along the gamma X path, and I'm going into these electron pockets, and what it's telling me now is that I have a strong dispersion here, which is what I was expecting, because I'm moving along this path. And therefore, with that, you get information about how your electronic structure looks like, where in fact where are the electrons mostly basically having transport, and you can start here now if you want to talk about, for instance, magnetism. Here you can, what I did is I displaced, you see that if I displace this by basically a commensurate vector in the lattice, I just can fit perfectly the Hall pockets to the electron pockets. And this is telling you the system has an instability towards magnetism. If you have some question on that, I can tell you more. Is it clear what I'm saying about these nesting properties? So this was one of the first things that one was observing in these materials, whether nesting was an important ingredient for describing the magnetism that is in these materials. It is, but you cannot make it general for all the systems, but there is a lot of nesting in this system. So you see that even if this looks ugly in the sense it looks just basically spaghettis, you can get a lot of information about that. Also the nature of these bands, whether they are D bands, P bands, what kind of D bands, is telling you a lot about what's going on in the system. Another quantity that is also very important is what we call the density of states. So how many states for a given energy are available to the system. Sorry, it's not a very good picture, but let me put myself here at the Fermi level, and you see that we have basically iron states near the Fermi level and a little bit of arsenic states, and then you can start by analyzing whether you have instability. So we know that if we have at the Fermi level very high density of states, this is telling me the system is near some kind of instability. So there will be either magnetism or a distortion to get rid of this very high number of states at the Fermi level. So this is what we call the Stoner criterion. Okay. So, since I don't have much time, I think my time is over, let me tell you a little bit about the drawbacks. So, this, as I say, it's a very powerful theory, but you saw where we do the approximations. We do the approximations in the non-local exchange, and we do the approximations in the electron correlation. This is this exchange correlation function. There is where we do the approximation. And there are many systems that are not correctly predicted. For instance, let's take all these oxides. These systems are not insulators, so they are insulators because Coulomb repulsion is very strong, and therefore they are insulators. And if you do a DFT calculation, you will get it metals. And you will get it metals because we are not describing this properly. Or in the case that I was showing to you, these iron-based superconductors, these are indeed, they are metals. However, they are in fact correlated metals. So if we compare these band structures that we obtain from DFT with, for instance, angular resolved photoemission experiment measurements, they don't fit. We have a lot of band renormalization that is not taken into account by DFT, and this is telling us that I'm not yet describing properly the correlations in this system. So how do we cure that? You stop me, Herman, when you say I'm done, you stop me. So I can continue that tomorrow. So we have, if you want, I can stop here. So tomorrow I can show a little bit about that. We can cure that, and the simplest cure is this LDA plus U, where we introduce correlations in a mean field way by introducing an extra on-site term like we do in the Hubbard model. There is a much better approximation, which is combining DFT with dynamical mean field theory. I can tell you some words tomorrow. And there is the third one, which is combining DFT with effective methods. But my time is over. I stop here, and your questions are welcome.
Thank you very much. Thank you very much. So questions.
Which phase diagram? Which one? Yeah.
Basic question. How do you recognize the different states here? Like, magnetic.
Okay, so first of all, how do I recognize whether the nature of the states? Okay, so if you remember, I started with these wave functions, and in these wave functions, so this is my basis set, okay? Here, in my wave function, this wave function has all the information, so these are spherical harmonics, have all the information of your electron, what kind of electron is. Is it a dx squared minus y squared, a dx, y, a d? So you do have this information, and therefore when you solve the equations, basically the wave function and the associated energy have the information because they have the quantum numbers. You see these quantum numbers, L, M, these are the quantum numbers of the orbital, and so these are, when you think about the quantum numbers, the principal quantum number, then you have the quantum L, which tells you the orbital, M, which tells you, in fact, which, and S, which is the spin. You do have in your solutions all this information. So your Kohn-Sham energies have basically these quantum numbers in it. So that's why I can identify, so in fact I should have written here K, L, M, so that I know exactly which is the nature of this band. That's why I can answer that. And the second question was magnetism. What you asking?
Like superconducting states.
Okay, from here I just did normal state. DFT is for understanding the normal state. If I want now to describe superconductivity, there is, in fact, only for the case for conventional superconductors, where you can also with DFT calculate the properties of conventional superconductors. And this has been done by Hardy-Gross in Halle, where they basically write exchange correlation functional for describing superconductivity. How do we do that here for unconventional superconductors? Now, for unconventional superconductors, we go from the assumption that the unconventional superconductivity is mostly driven by spin fluctuations. So if we make this assumption, what we do then is, indeed, we take the information of the DFT, we derive effective models, and then we treat them with methods to obtain superconducting properties. So, but from DFT directly, you cannot obtain unconventional superconductivity. Okay, it's for normal state.
More questions, comments? Yeah.
Just one question about, there was this recent discovery of superconductivity and twisted bilayer graphene.
Yes.
How can you see, do you think this can give some ideas
Okay.
about how these complicated superconductors work?
Okay, I'm not a specialist on twisted graphene, but just put it out of the. No, I can tell you what I know about them, but I'm not a specialist. So I hope that I say nothing wrong. Okay, in this twisted graphene, basically what is interesting is when you go to this magic angle, if you look at the band structure, you get basically flat bands. This is extremely important because flat bands, it's telling you, like here, I have this flatting, your electrons are almost localized. From the moment that you start localizing electrons, because you have this basically inexistence of bandwidth, Coulomb repulsion is going to be very important, even if you are treating p electrons in the case. But Coulomb repulsion becomes important because your bandwidth is almost inexistent, because they are almost localized and then they feel each other. So now for twisted graphene, so this is one issue. This you can see it in the DFT calculations. However, it's not as simple in twisted graphene, because when you do this twist, it's an incommensurate twist. If you want to do it in a microscopic type of calculation, you really need large and large and large supercells. There are a couple of groups that have done that, like Liang Fu has been trying to do that, and Andre Bernebig. There are some groups that have done that, but most of the groups, what they do is they work with a continuum model. Since after all, when you find when you want to describe what basically is driving this phase diagram, the distances are very large, so continuum model is fine for that. But I must admit that I haven't put myself too much onto this subject. But for DFT, you really need very large supercell calculations.
Yeah, okay.
When you just, in this figure in the Fermi surface, when you show the displacement of
Yes.
the vectors
Yes.
from the
This is the pi. Yes.
the hole pockets and the electron pockets.
Yes.
And you say that when you match each other,
Is
like the figures, it's more instability. For me, it's always difficult to understand why I have more stability or more instability.
Okay.
When I look at the
Yeah.
displacement and the
Yeah, because basically if you think, let's put ourselves in the K space, okay? And now let's think about the electrons scattering in the K space. So I'm scattering here now. Electron is scattering here. The electrons are scattering between hole pockets and electron pockets. Now, if you have basically, this is a pi vector. So it means that there is, for this scattering, the electron doesn't need any energy. And if the electron doesn't need any energy to do this process, this is what we call instability. When you have a lot of, you can use the word of degeneracy if you want, but if it doesn't cost you energy, then the electron is going to be basically in this situation, this scattering is going to be important. And then what happens is that the system then goes into a magnetic phase, which has exactly this. So it magnetically, or let's put it, the spin system basically adapts to this kind of scattering, so that there you go into a more stable state than what you would have if the electron would be scattering in this nesting vector. So basically the idea is, so when we talk, for instance, in magnetism, when you have a lot of states that are available to your system that they have exactly the same energy, the system is frustrated, right? So because it cannot decide, and this is this is what we call a very unstable situation, because the system doesn't like to be. I mean, you don't like to be frustrated, right? If you have to do 10 decisions and you don't know which, this nature is the same. It's just, it doesn't like to be in this frustrated situation. So it's enough to have a small perturbation in the system to just bring the system into one state that is lower in energy than all the other ones. And this kind of effects here can be thought in this way. You have these very special vectors where the electron doesn't need any energy to go in from electron to hole pocket, and therefore the system will try to use its internal mechanisms to just pin the system into a lower state energy state, which in this case will be the pi or the pi zero, depending on which unit cell you're talking about, which will be the stripe order that the systems form. This is what it means. Paul?
Can't I think about that energetically in a simpler fashion?
Probably,
Because
yes.
With a single wave vector, which is the magnetic ordering, I'll open a gap on those Fermi surfaces and lower the energy.
Yes.
So it just becomes energetically.
Yeah, that's what I'm saying. Yeah, well, okay.
Oh, okay, but I mean, in terms of energy,
You open.
Energy is just very simple to think of. So with a single wave vector, I gap those Fermi surfaces and lower energy. So it's
It's the Piles mechanism.
Exactly.
It's the Piles mechanism.
IQ.
Exactly. Make it general, but yes, thank you. This is.
Okay, I have one question. So, several months ago, there are several books that use symmetry arguments to predict situations in the band structure.
Yes,
that
yes.
might be interesting. Right?
Yes, yes.
Well, then they get out a list of new materials which seem to be topological.
That's band topology. Yes.
Some of those are, however, known as normal beta, so it doesn't always work. So, I mean, how should we take at face value these predictions?
Oh, I think, okay, so these predictions, so you see, all these band structures, they have well-defined symmetries, they have everything in it because of what I was showing to you. I have all these quantum numbers and I am already defined in a certain symmetry. So now what all these groups have been doing is, okay, so And this is in fact very old. There are very old papers already at the beginning where people were doing band theory. There were no computers, so they had to do everything by hand. They really needed a very good knowledge of group theory, magnetic groups. All this was put into this type of calculations. Nowadays we have the computers, we press the button and everything comes out. So that means that indeed I can follow and I can know exactly when I have here crossings, okay? So these crossings here,